Hello, my name is Michael Dick, and I'm a research scientist with Green Imaging Technologies. Welcome to our webinar on gas isotherms via NMR. This is something we've been working on for the last year at GIT, and we've recently implemented it into our software. Let's begin by talking about the importance of gas isotherms. Gas isotherms, which are a measure of the total gas content as a function of pore pressure, are used to assess a reservoir's profitability. The total natural gas content in a shale consists of both absorbed gas in the pore spaces of the shales and adsorbed gas on the surface of the shale matrix. The absorbed gas content follows the ideal gas or van der Waals gas equation as a function of pressure and is plotted, for example, here in green. Conversely, the rate of increase of adsorbed gas, which is plotted here at rate as a function of pressure, decreases as the pressure gets higher. This is because the number of positions for adsorption are consumed as the pressure decreases. Then the total gas content is simply the sum of the absorbed and the adsorbed gas content, and it's, for example, plotted here in blue. Traditionally, gas isotherms are measured by exposing the core to helium and methane at ever-increasing pressures while tracking the volume of gas absorbed or adsorbed. These experiments often involve destruction of the core, and they provide no information on the pore size distribution. So if we could do these measure these gas isotherms via NMR, it would be good because we won't have to destroy the core, and we will get pore size information from the NMR data. This slide shows an experimental setup used to record the gas isotherms via NMR. The shale core is initially confined into one of our Oxford Instruments P5 overburden cell. In this case, fluorinert was used as to provide the overburden pressure of 2300 psi. The probe is then inserted into one of our 275 geospec magnets, and then the inlet and outlet lines are connected to the gas manifold like shown in this diagram here. The experiment then begins by evacuating all the air from the rock using this vacuum pump here. The air is then replaced with methane at several different pressures. Once the methane has reached the given pressure, we begin to record T2 distributions at each of these different pressures. In this case, at pressures ranging from 0 to 2000 psi. The pressure is very important in this experiment, so we continually measure all the pressures in this experiment using various transducers located throughout the experimental setup. All the pressures are logged via an Arduino-based data acquisition system, which pushes up the pressures to an internal website in our lab. The internal website is monitored via server application, which logs the pressures every minute. In addition, because these experiments can sometimes last days or even longer, our Raspberry Pi computer also monitors the internal web page for the pressures, and it controls the confining pressure by turning a HPLC pump on or off depending if the pressure is too high or too low. The next slide shows some sample information and NMR parameters used for all the data we recorded. So first you can see here that for our first sample was a Barnett shale shown here, and first thing we did was we heat shrunk it between two end caps like shown here before it's inserted into our OB cells like the one shown here. So this slide shows a typical T2 distributions recorded for the shale sample at a methane pressure of 2000 psi. The trace shown in red was recorded within a few minutes of the initial injection of methane. The blue trace was recorded several hours after the initial injection of methane. As you can see, and as expected, the amount of methane increases as time goes on. This will become more obvious on the next slide, where we're going to background subtract the background signal of the probe, which is shown here in black, from the red and the blue traces. So let's go ahead and see what that looks like. So now you can really see that the amount of methane definitely increases over time when you fill it into our rock. That's as expected. And then it's the area under these curves that is the amount of methane observed. And this amount of methane observed right now is in equivalent water signal because our spectrometer has been calibrated in units of equivalent water. The other thing to note here is that neither the small nor the large pore network are filled preferentially as a function of time with methane at any given pressure. So then the question became, how long does it take for the methane to fully fill the shale samples? So to do this, we repeated our T2 distribution measurement over and over again for several hours, up to a day in fact, at various different pore pressures. And what we found was that it actually takes about 4 hours before the amount of methane stabilizes. So once you have this data, retrieving the gas isotherm is pretty straightforward. You simply take the amount of methane observed for each pressure after 4 hours, and that's the data you need to plot your gas isotherm. So you plot the gas content versus the pore pressure. But right now the gas content would be in units of equivalent water volume. So we need to convert that to gas content in units of SCM cubed versus centimeter cubed. So to do that, we use this equation right here, where we use the bulk volume of the rock, the standard temperature and pressure of 25 C and 1 atmosphere, the volume measured from this equation, from this data, the hydrogen index, along with the experimental pressure and temperature. And when you do that, you get a gas isotherm like the one shown here in blue. So that's the total gas content isotherm. So now the question became, how do you derive the absorbed and adsorbed gas content from this data? So to do this, we first calculate the absorbed gas content, and we do this by taking the pore volume of the rock, which was measured in a separate experiment with 100% brine saturated rock. We then couple that with the van der Waals gas equation to get the gas content as a function of pressure, and that's in green. That's the absorbed gas content. And then to get the adsorbed gas content, you simply take the blue trace, which is the total gas content, minus the absorbed gas content, and the remainder is the adsorbed gas content. And when you do that, you get a gas isotherm that look like this for our first rock, and they have the expected appearance. So we did a second sample. It was also tested. This slide shows the sample parameters along with the NMR parameters employed for testing. The difference with this sample as compared to the first sample I just talked about is that the sample was fragmented. So in order to test this sample, we had to build a new Teflon holder. This new core holder was 1.5 inches in diameter with a 1-inch diameter hole in it, into which we inserted the fragmented samples. We then load this core holder into our 1.5-inch diameter overburden cell as if it was a 1.5-inch diameter core sample. So this slide shows the experimental procedure and setup was also modified slightly to accommodate the fragmented sample. The methane gas was again introduced into the pores of the sample, changing the pore pressure from 0 to 2000 psi. This time, however, the fluoriner was eliminated from use in the experiment. Instead, it was replaced by filling the confining volume with methane directly at the same pressures employed to obtain the gas isotherm. As a result of no fluoriner, however, we didn't need to have a pump to control the confining fluid, so you can see we eliminated the confining fluid pump here. But again, the pressures were important to this experiment, so we continued to log them with our Arduino-based data acquisition system and a program running our server which logged the pressures. So we followed the same procedure as we employed for the last sample with this sample, where the T2 distributions were measured as a function of time and repeated at different pore pressures of methane. Also, the background spectrum at 0 psi CH4 was also recorded. The difference this time was that because we used methane as the confining fluid, we had a lot of free methane signal like that shown here in red and blue. So we needed to apply a cutoff in our T2 spectra so that we didn't use any of this free methane information in derivation of our gas isotherms. So to do that, we apply a cutoff line at around 200 milliseconds. So anything to the right of that cutoff line we don't use, we eliminate, and we don't use in our analysis, whereas anything to the left we do use in our gas isotherm analysis. So we then, with that, once we apply that cutoff, we take this information and we do the same analysis as I just explained. And when you do that, you get a total gas isotherm like the one shown here in blue. Then to get the absorbed gas isotherm, which is shown here in green, we simply again use the van der Waals gas equation and the pore volume of the rock, which once again was measured in a separate experiment. That gives us the total, the absorbed gas isotherm right here. And then to get the adsorbed gas isotherm, which is shown here in red, we simply take the total gas isotherm, subtract the absorbed gas isotherm, and the result is the adsorbed gas isotherm, like the one shown here in red. So moving on, this is our last slide, and it's just simply a movie of how you can implement or create a gas isotherm in our GIT system software version 9.0. So I'll go ahead and start the movie. So the first thing we do is over on the left tab, you select gas isotherms. Next, you enter all the appropriate sample information here, like bulk volume, pore volume, etc. You then go ahead and select the background pressure measurement or the 0 psi measurement from your list of T2 measurements. And next, you go ahead and select all the measurements done at each of the pressures, in this case from 500 to 2000 psi. You then edit the appropriate pressures to make sure they match the appropriate value. So for example, this one was done at 2000, so the pressure over here better say 2000. That's what I do. Change this one to 1500, 1000, and finally 500. Once you've done that and make them match like they do there, you simply hit the run button, and then it goes off and creates your gas isotherm like the one shown here. So that's the end of our webinar. Thank you for joining us for this explanation. So if you have any questions, feel free to contact us at via email at info@greenimaging.com or visit our website greenimaging.com. Thank you.